development of science education in South Africa. So he's one of the volunteer coordinators of the Institute of Physics Africa program. So let me, without further ado,
well, thank you. It's always a delight to be back in this wonderful country, of which I am so extraordinarily fond. I want to speak this week about weapons of mass destruction. This is a topic of enormous importance because there exist on Earth enough nuclear weapons to kill every human being on the planet several times over. Okay? Moreover, there is a man who will take control of about 5,000 of these next Friday, who has first encouraged proliferation by encouraging Japan and South Korea to have nuclear weapons, and who has stated that we have so many of these things, why don't we use them? No such weapons have been used for over 70 years, and there are a few people in this room, including me, old enough to remember when they were used. But the two bombs that the Americans used on Japan were virtually firecrackers. They are so tiny compared to what exists today. I worked for several years on problems of weapons non-proliferation, but nonetheless there are at least 8 countries in the world today which possess nuclear weapons. Their importance, their growth is such that perhaps they have prevented war because, or at least they have prevented world wars. There have, at least so far, there have been no conflicts between the major superpowers because people have come to realize that these weapons there are no winners in that case. There are only losers. These weapons kill everybody. The situation could be and could have been and still can be very different, and I want to outline this, of course, and the problems involved. Now, I started my university studies back in the 1950s, and every professor in every class I ever took or every research project on which I ever worked had been doing research during the Second World War. They worked on things like the Norden bomb sight, or on radar development, or on the development of shaped charges which allow the piercing of armor on the fronts of tanks, or, of course, at Los Alamos on atomic weapons. The pressures at that time on people are not easily understood by generations too young to remember those days, and I'm absolutely delighted that there are a few people here who are too young to remember those days, because they need to understand. But the threat of Nazi Germany, of course, was enormous. The war was seen really, and probably really was, seen as a means of determining the future of civilization. There was a pandemic of man-made death in the 1940s. The British and the Americans were fighting in the Pacific and in North Africa. At the time when Los Alamos was created to build the bomb, Britain was suffering the Blitz, and much of continental Europe was occupied by Nazi Germany. The scientists in the UK and in the US were largely men, but not all. There were some women involved as well. We're very well aware of the caliber and the abilities of their German colleagues. Due to the Nazi threat, 111 scientists and mathematicians had left Europe. Among them, there were 33 Nobel Prize winners, among that 111, which is quite a remarkable number. Some came to the UK, mostly they came to the US. There were a few non-science people who are very famous, such as Hannah Arendt, Kurt Weill, Ludwig Wittgenstein, for example. Many of these people were Jewish, fortunate enough to get out. All the scientists were aware that nuclear fission had been discovered in Germany and that Germany was ahead. The fear and the pressure on people was enormous. They worked as hard as they possibly could under extreme handicaps. Those at Los Alamos were very well aware of the awesome scale of the weapon that they were building. But they ceded control over the development and the use entirely to the military. And they probably had no choice in doing that because the amount of money invested was truly enormous. In today's terms, the U.S. put approximately $40 billion into developing the atomic bomb. And I doubt that the U.S. government would have given that amount of money to a group of weirdo scientists. But still, the control was given up without a great deal of thought. A few people, as we shall see, did object and did think, and many people suffered serious moral crises after the war when the consequences of what they had done became obvious. I worked with a man in about 1970 who was a major player at Los Alamos and whose life was basically destroyed. He never did a decent piece of work after that, although he was an extraordinarily bright and very nice man. The military had some idea at a fairly early age that the Germans had stopped work on the bomb. That information was not made available to the scientists at Los Alamos. When it did sort of leak out in late 1944 and early 45, only one man left Los Alamos. I will talk about him. The death of Franklin Roosevelt may have made a crucial change. We just don't know what would have been done had he been alive. But the ethical questions of science are extremely serious. They're not so common today in the world of physics, but they are terribly relevant, I think, in the world right now of biology, because we have the ability to edit the human genome, and that could eliminate major diseases. It could destroy the entire human population of the Earth. There are ethical questions about science which are very serious, and so the summer school and I have arranged an extra session on Saturday at the same time, probably here, which will be an open discussion rather than me talking about how people feel about the ethical situation between science and society, and I hope many of you can come to that. At the beginning of the 20th century, there was the greatest revolutionary change in the history of physics, and maybe in all of the intellectual development of the human race. Much of it began with Albert Einstein, who in 1905 published a series of papers in which he gave definitive proof of the existence of atoms to the last remaining few skeptics who did not believe in their existence. He created the theory of relativity, changing entirely our understanding of space and time, and he began the study of quantum mechanics by showing that that light could have both a wave and a particle-like nature at the same time. And this last discovery led to the invention of quantum mechanics, which we'll also talk a bit about. And it's a bit ironic that quantum mechanics, which was basically invented by Einstein, became very unpopular with that man. In the decade following his 1905 work, Niels Bohr discovered the laws governing the structure of electrons in the atom, and hence the entire understanding of the theory of chemistry. Ernst Rutherford discovered that the atom had a nucleus, which was incredibly small, even compared to the incredibly small size of the atom. And I will talk also about that to some extent. And in the decade of the 1920s, the complete theory of quantum mechanics was developed. Back in 1912, Kaiser Wilhelm II, who was the eldest grandson of Queen Victoria, was convinced to establish scientific institutions for the study of both chemistry and physics, the first two of 7 that he rapidly established in Berlin. One of the first chemists to work there was a young German named Otto Hahn, who had worked originally in England with Ernest Rutherford on the chemistry of radioactive elements. He returned to Germany in 1906, and by 1907, he was what is considered a radiochemist, which is a person who works primarily in the chemistry of radioactive materials. This was not popular with his chemistry colleagues, and so he often attended the physics colloquia where people were more congenial. And it was there that he met this young Austrian woman, Lisa Meitner. They became friends, and they worked together on experiments for years. Meitner was a Jewish Austrian scientist whose entire family had converted to Christianity early in the century, a fact which made absolutely no difference to her survival following the Anschluss in 1938. I spoke at length about her 2 years ago when I talked about women in physics and astronomy, and she is one of my great heroes in the world, and a woman I have, despite the fact that she's dead, I have quite a crush on nonetheless. The director of the institute at that time was an irascible German Jew named Fritz Haber. Haber had become famous, and he in fact won the Nobel Prize, for being able to extract nitrogen from the air in order to make ammonia. During the war, the British blockaded Germany, and that meant that the importation of nitrates, which had come from Chile originally, became impossible. It was because of Fritz Haber's ability to make nitrogen out of the air that allowed the Germans to build armaments and munitions and continue the war effort. He also was the inventor of poison gas, so that chlorine, phosgene, mustard gas were all things that he had invented. Haber's wife, who was also a chemist, begged him to stop, and he refused. She became very depressed and eventually killed herself over that difficulty. While Haber was busily inventing poison gases, in Britain, a chemist friend of Ernest Rutherford's in Manchester discovered a way to make artificial rubber. His name was Chaim Weizmann, and he discovered this process and was a close friend of C.P. Scott, who was the editor of the Manchester Guardian and a good friend and advisor of the Prime Minister, Lord George. The British government was so grateful to Weizmann for this discovery, he was promised an honor. That honor turned out to be the Balfour Declaration, a commitment by the British government which led to the establishment of the State of Israel. In Hungary, during and after the war, an exceptional generation of Jewish scientists grew up, all of whom left Hungary at a young age, all of whom contributed enormously to the downfall of Nazi Germany. I'll just read a list of their names. Leo Szilard, Theodor von Karman, George de Hevesy, John von Neumann, Michael Polanyi, Dennis Gabor, Eugene Wigner, Edward Teller. 3 of them, de Hevesy, Gabor, and Wigner, won Nobel Prizes. They were a truly remarkable group. Leo Szilard the man I want to talk most about, was born in Budapest in 1898. He served in the Austro-Hungarian army during the war and was saved by getting the Spanish flu. Now, that epidemic of Spanish influenza killed more people than were killed in the First World War. But it did not kill him. It did, however, keep him from the front, which was very fortunate for him because the regiment in which he was completely decimated in a battle. He was an enormously precocious student. There's a picture of him as a young age. He won the largest prize in Hungary at the age of 18 in mathematics. He was, however, denied entrance to Budapest University because he was Jewish, even though on the form under religion he wrote Calvinist, made no difference. So he headed to Berlin to study. Now, in those days, universities were very different. They were peripatetic, and one could wander around from university to university, depending on the subject one wanted to study, the professor one wanted to listen to. I've put, by the way, a little Hungarian flag at the top, so just... because of his wandering, he studied under Einstein, Max Planck, Walter Nernst, James Franck, Max von Laue, the names of the greatest giants in the history of physics. He also met other Hungarian students there, Wigner, von Neumann, Dennis Gabor, again, people who have gone on to do great work. His PhD dissertation was on a subject called Maxwell's Demon, which is about information, and during which he created the entire discipline of information theory, which has come to be the basis of computer logic. He never followed that up. He had an enormous number of ideas which he did not follow or publish, and we find in his private papers the invention of the cyclotron and the invention of the electron microscope, both of which gave Nobel Prizes to the people who discovered it next after him. But he was not a shy man, and he had a letter from Albert Einstein complimenting his PhD dissertation, and so he asked Einstein if he could work with him, and they did work together. Somewhat later, in the late 20s and early 30s, Frédéric Joliot and his wife Irène Curie, the daughter of Pierre and Marie Curie, announced the discovery of artificially induced radioactive elements. Radioactivity had been discovered back at the end of the 19th century, but these were natural elements that existed on Earth. These people, for the first time, made artificially induced radioactive elements. Now, natural radioactive elements emit alpha particles. Alpha particles are really just the nuclei of helium atoms. They contain 2 protons, that's what makes them helium, and 2 neutrons, although the neutron had not yet been discovered, so people didn't know. They just knew it weighed more. They were bombarded aluminium foil with these alpha particles from radium, which they had a lot of because of Marie Curie, and they discovered that they could create elements that were themselves radioactive. That was the very first time. They made an enormous number of discoveries. They discovered the positive electron, and they discovered the neutron, and by the means of serendipity, they didn't understand what they had, and they lost the discovery. Those 2 discoveries, the positive electron and the neutron, won Nobel Prizes. They, however, also won a Nobel Prize for this artificial radioactivity, the Nobel Prize in Chemistry in 1935, so that Marie and Irène Curie are the only mother-daughter team ever to have won both Nobel Prizes. James Chadwick, who had been a student of Rutherford, and now was at Cambridge, seized on the results, repeated them carefully, and announced the discovery of a heavy particle similar to the mass of a proton. It turns out to be slightly heavier, and possessing no electrical charge at all. I don't know what that is. And this was, of course, the neutron. Now, here is the periodic table of elements invented in the 19th century by Dmitry Mendeleev, who made lists of elements according to their chemical properties, so all of the vertical columns have very similar chemical properties. Now, you'll notice, please, that there's a number in the upper left corner, 1, 2, 3, 4, 5, etc. And that is called the atomic number, and it is equal to the number of protons in the nucleus. So that one proton is hydrogen, and alpha particles, which are the nuclei of this element, have 2 protons. But there is another number down underneath, which, first of all, is often, except for this one, is often twice this for these first elements here, often about twice, but it's also a fraction, and by the time you get up here, it's much greater than twice the number. So for uranium, which is 92, the number here is 238, which is a lot more than twice 92. Why? Now, once the neutron had been discovered, we began to understand. So that, for example, carbon, which has 6 protons, that's what makes it carbon. The carbon that's in us, and we are largely carbon, has not only 6 protons, but it also has 6 neutrons in its nucleus, and that makes it called carbon-12. But there also is an atom of carbon, or nucleus of carbon, which has 6 neutrons and 6 protons and 7 neutrons, carbon-13, and 6 protons and 8 neutrons for carbon-14. Carbon-14 is radioactive. It has a half-life of 5,700 years, which makes it very useful for dating ancient materials, and some of you will know about that. These extra things, 7 neutrons, 8 neutrons, are called isotopes, and isotopes are defined on that handout sheet that I gave you, which has some technical terms explained. Now, Szilard was living in Germany in the 20s when there was, of course, catastrophic inflation going on in the country. But also the number of people living in that country were truly amazing. There was Mies van der Rohe, who built the first skyscrapers, Vladimir Nabokov, George Gross, Yehudi Menuhin, along all with this scientific aristocracy. Szilard became a German citizen in 1930, but when Hitler became chancellor in 1933, he went to the United Kingdom. And it was in London that he had his epiphany. This is described by Richard Rhodes in a book I recommended called The Making of the Atomic Bomb, which is an absolutely phenomenally interesting book. Szilard was irritated by a paper written by Ernest Rutherford, which said that we would never get any useful energy out of the atom. Then, as he described later, he was in London working at the British Museum in the reading room on a dreary winter London afternoon. And London winter afternoons are very dreary, which is why I'm so delighted to come to South Africa at that time. And he was standing at a traffic signal by Russell Square. I know exactly where that traffic signal is, and I irritate everybody I know by pointing it out every time we passed. That's Szilard's traffic light. And in Rhodes' words, he said, "Time cracked open for him, and he saw a way to the future, death unto the world, and all our woe, the shape of things to come." This was 1933, a year after the discovery of the neutron, 5 years before nuclear fission was discovered. He had the following insight. Neutrons are neutral particles. They can easily penetrate a nucleus because there's no repulsive force. If I shoot an alpha particle towards a nucleus, it's positively charged, the nucleus is positively charged, they repel. But a neutron doesn't have that force, it can get in. And maybe, he said, it could make the neutron unstable, the nucleus, a new isotope of some element, unstable. And if that nucleus became unstable and fell apart, energy would be released because the mass of the daughter products would be less than the mass of the parent product. And energy and mass are the same thing, E equals mc squared. Moreover, if the decay of this oscillating nucleus released, say, 2 neutrons while it fell apart, then each decay creates 2 neutrons. Those neutrons would each then cause 2 more nuclei to decay, each releasing 2. That's 4 neutrons. Then they release 8 neutrons, 16 neutrons, 32 neutrons, a chain reaction. He realized the implications, positive and negative, of the chain reaction. He went on to write, "I didn't see," the following words, "I didn't see at the moment just how we would go about doing this, but the idea never left me." Really, he was a man of amazing intelligence and insight. There he is, somewhat more rotund. Now I want to turn in detail to the life of the man I believe to be the greatest physicist of the 20th century, Enrico Fermi. I admire Fermi for many reasons because he was the only great genius who was able to do both experimental and theoretical work in science, and also because he was an exceptional teacher. Much of the information that I know about Fermi comes from his wife Laura, whose existence has played a huge part in the history of the 20th century. Here's a picture of Fermi as a little boy. That's Enrico. That's his older brother Giulio, and that's his older sister Maria. They are, he's 1 year younger than she, he's 1 year younger than he. He was, this young boy, Giulio, to whom Enrico was very much attached, died at a fairly young age in an accidental way in an operation, what was meant to be an operation, a minor operation. And Enrico assuaged his grief by study. And he studied primarily mathematics and then science. And he had very little money, so he was greatly handicapped because he had very few books. So he scoured all of the used bookshops in Rome, and he read at one time a 2-volume book on mathematical physics of waves. And when he finished, he mentioned to his sister Maria, "Oh, I just noticed that this book was written in Latin. I hadn't noticed that before." He and a good friend did all kinds of experiments together. They made a really accurate measurement of the Earth's magnetic field, and they investigated the physics of the gyroscope. Now, one of Enrico's father's friends noticed this boy was tremendously interested in science, and he gave him problems to solve, which he did, easily and quickly. And so he made the problems harder and harder until they came to be a level at which the adult couldn't solve. Enrico continued to solve them easily and quickly. And so he lent Enrico books in a careful order to increase his knowledge at a reasonable pace. And when he finished secondary school, this gentleman told Enrico of a special school in Pisa called the Scuola Normale Superiore in Pisa, which was very good at science. And he encouraged Enrico to apply for a fellowship. And so he sat the entrance exam and scored perfectly on it. And so he was called in by the examiner for an interview, after which he was told that, young man, you are really quite exceptional. He received his doctorate in physics magna cum laude in 1922 when he was 21 years old. And then he returned to Rome. Shortly thereafter, the fascisti under Mussolini entered Rome. The government collapsed. Mussolini took control of the country as dictator for the next more than 20 years. Meanwhile, Fermi had won a fellowship to study in Göttingen under Max Born. And he was a bit shy in that company because Göttingen was the center of the intellectual scientific world at the time, with Born, Heisenberg, Pauli, Jordan, the absolute giants creating quantum mechanics at the time. And he spoke German reasonably well, but nonetheless, and he was very fortunate, of course, because I already mentioned the great inflation. He had money from Italy, so he was quite well off. So when it expired, he returned to Rome and was hired on at the university. And he met a young woman named Laura there in 1924, and she was only about 16 when they met. 2 years later, he was a professor at the university, the youngest. Laura Capon became a student at the University of Rome in 1926. She was, of course, rather in awe of that the student had as a student for her professor, but she continued the friendship with Enrico, and this involved walks and outings. Fermi was a very active and very competitive outdoor type of person, something he repeated at Los Alamos when he was there in the 40s. Every time there was a dangerous experiment done, he went off with his friends and climbed a mountain. By 1926, at age 25, he had already published 30 papers, a few on experimental work, with the majority on theoretical subjects. He had published a paper called On the Quantumization of a Perfect Monatomic Gas. I won't bother you with a description of what it is, but it was a paper which described the statistics of atoms, and it gave rise to what are now called Fermi-Dirac statistics. And particles such as the proton, the electron, the neutron, us, are all called fermions in his honor. He was, and it is his theory of electrons which determine chemistry, and which the chemistry determines life, and life is us. So it's really quite something. Social connections led Laura to various dinners where they became closer and closer. And also, she met a man there called Emilio Segre. Segre became a physics student by asking an enormous number of questions, such as, who is this guy Bohr, when Niels Bohr came to visit? Only the greatest scientist, maybe one of the people of the order of Galileo or Einstein or Newton. And what is the Compton effect? And what is Planck's constant, etc.? He was very good at asking questions. And I find this amusing because in the early 60s, I was a graduate student working at the University of California, Berkeley, and Segre was a professor there. Now, I didn't know this man by sight, but so I'm working with a bunch of Berkeley graduate students, and this short little guy comes up wearing a jacket and ties, which is completely unheard of in the physics community. And so I didn't know where he was, and he sort of asked me, what is this stuff you're doing? And so figuring he didn't know anything, I described in detail what the apparatus. Meanwhile, the Berkeley graduate students were all there, rigid with attention. And when he left, they told me who that was. And, you know, I was a little embarrassed, but they said, no, that's how he learns things, by asking graduate students who don't know who he is, because otherwise he doesn't know anything. Fermi was teaching the new quantum mechanics to his student, and he was very good at it. And because of this, he was given the nickname of the Pope. Now, by 1927, it was clear there was a romantic attachment growing between Enrico and Laura. And in July 28, they were married. The ceremony was a non-religious one because Enrico, of course, as normal Italian, had been brought up a Catholic. And Laura's family were what she called non-observant Jews. This was no help at all a decade later when Mussolini brought in the Nuremberg racial laws into force in Italy. And this, as we shall see, affected the history of the world. Here is a picture. I like this picture. There's Enrico. There is Segre. He looked quite different. There's Eduardo Amaldi, a really, truly, I mean, these are all immensely famous people. He won a Nobel Prize, he won a Nobel Prize, etc. Fermi was very famous for informal teaching methods. He was a fine teacher, as I said. And in physics, people calculate things. And mostly we calculate things very exactly. We know some of the constants of nature to 10 decimal places. But sometimes it doesn't pay. Oh, I'm sorry. I wanted to show you, there is Enrico and Laura, and there they are at their wedding. That's her father in the naval uniform. There's Laura, there's Enrico. But sometimes we want to just approximate things, and Fermi was an expert at that. One of his most famous problems, which I think is known to every physicist in the world, is he was teaching at the University of Chicago. How many piano tuners are there in Chicago? Now, you could go in the days of telephone catalogs, you could go and look that up. But that's not what he meant. What he wanted people to do was say, how many people live in Chicago? What fraction of people have a piano? How often does a piano have to be tuned? Therefore, you can estimate how many piano tuners there are. When I do that calculation, it's 50. Okay, there were about 65 piano tuners in Chicago. So, you know, it's called an order of magnitude calculation. It's not 500 and it's not 5. And so in science, we do either one. We do exact calculations when necessary. We do approximate calculations otherwise. Fermi was the only physicist elected as a member of the original 30 people when Mussolini created the Italian Academy in 1929 as a tribute to fascism. Fermi did not like such a fuss, but there was a real advantage for him because there was a salary attached, which was 1.5 times his university salary and paid in addition. So that for the first time, his family was reasonably secure financially. In 1930, he was invited to the U.S. to teach in a summer school at the University of Michigan on the quantum physics of radiation. Now, his English was learned in the way he learned foreign languages, and he was a very interesting man. You take a popular book, and you read the first 50 pages of this book with a dictionary, translating every word as you go. Then, after 50 pages, you just read the rest of the book. Then you do this with, say, 10 books, and that's 5,000 pages with a dictionary. By then, you've mastered the language. Well, he used Jack London novels in English. This method had worked reasonably well in French and German and was absolutely useless in English. When he got to New York, New York was a shock to him because he couldn't understand the accent, in New York is not so easy. So he had a hard time speaking, and he could not understand spoken English at all. Now, he had to lecture for 2 months at the University of Michigan. He was very fortunate because he had good friends, two Dutch physicists, Samuel Goldschmidt and George Uhlenbeck. We will meet Goldschmidt later on, who helped him. They were Dutch people settling in the U.S., and they helped him with his pronunciation. And so at the end of 2 months, he was pretty competent. Fermi met them back in 1924 when he was in Leiden, where they were both working for Paul Ehrenfest. Ehrenfest was a very great theoretical physicist, a Viennese Jew, who eventually had found a position in Leiden because he could not get a job in Austria. He had a terrific career, but he suffered from severe depression, so great that his friend Einstein wrote to the university for help. And he got help, and it didn't help, because he eventually shot and killed his son, who had Down syndrome, and then killed himself. It's a great tragedy. Fermi returned to the U.S. in 1933 and 35 and 37. Laura didn't accompany him because by that time she had small children to care for. Now, back, as I mentioned, in Paris, the Joliot-Curies had discovered artificial radioactivity by bombarding aluminium with alpha particles. Now, alpha particles have 2 protons in them, and therefore they're approaching the nucleus of aluminium, which also has positive charges, and they're repelled. It makes it hard for the alpha particle to get in. But Fermi had the idea that maybe he could use neutrons, which have no such charge, and neutrons have a lot of advantages, of course. They also do not lose energy as quickly as alpha particles. Now, alpha particles, as I said, have 2 positive charges. So they come in and they're going by nuclei, by atoms. And mostly the nucleus is so small that mostly the alpha particle just whizzes right by the nucleus. But the electrons are all over the outside, and so the alpha particle goes by the electrons. And because it interacts electrically with these negative charges, sometimes it knocks them off. Okay? And then the atom, aluminium or whatever it is left without an electron. This process of knocking electrons off is called ionization. And because they are doubly positively charged, they ionize very quickly. It means that they do not penetrate material very far before they lose all their energy. For example, an alpha particle would not penetrate this piece of paper. It does not penetrate human skin. I could hold an alpha particle in my hand without any damage to me. However, they are deadly if ingested, because they ionize very rapidly. If you put them on the inside of your body, that's a very serious effect. So breathing them in or swallowing them is a very bad thing to do. This was demonstrated, unfortunately, in the death of Alexander Litvinenko back in 2006. He died by ingesting polonium-210. Polonium is a common alpha emitter, and this was put in a cup of tea, which he drank. And this caused huge damage to his body, a severe radiation poisoning. And even though the symptoms were of radiation poisoning, and he was checked with a Geiger counter, it showed no effect because they couldn't get out of his body. Eventually, just before he died, they tested his blood, which was full of radiation. Neutrons do not easily ionize because, as they penetrate, because they're not charged. and therefore they have a much greater distance or range in material and a much higher chance of a collision with a nucleus and the possible creation of an artificially induced isotope. There's a disadvantage, of course, to using neutrons, and that is they are not naturally produced by anything. Alpha particles come out of lots of heavy radioactive materials, such as polonium or radium, but neutrons come out of nothing. To create neutrons, Fermi's shown alpha particles on various materials trying to produce neutrons, and it took about 100,000 alpha collisions to produce one. Now, when you put an alpha emitter, as he did together with beryllium, you get neutrons. Here's the periodic table again, and here's beryllium. Notice beryllium has 4 protons, but it has an atomic mass of 9. That means it has 5 neutrons along with 4 protons. One of those neutrons sort of sits on the edge, and when an alpha particle comes in and bangs it, the neutron is knocked out. So Fermi was a very methodical worker, and so he then took these neutrons and shone them on hydrogen, nothing happened, helium, nothing, lithium, beryllium, boron, etc., nitrogen, oxygen, no effect, no artificial radiation isotopes produced. And then he got the fluorine, and he made all sorts of artificial elements in fluorine. So there was a big effect with fluorine. Now, what he wanted to do was test every element in the periodic table in order. Okay? Now, some of these elements, ruthenium, molybdenum, niobium, etc., some of these are very rare and they're hard to get. And he didn't know how to do that. But Emilio Segre, who was working with him, was the son of a businessman who was quite used to negotiating and purchasing and money. And Segre did a very good job of finding all of these elements. So they irradiated various elements with neutrons, and then they checked to see whether they had radioactivity afterwards. Now, you can't check the element directly in the same laboratory where you do the experiment, because you're starting with a radioactive source. You hope you've got a radioactive effect. You don't know if you put a Geiger counter on something whether it comes from the source or from the material. So they set up a separate lab in another room, 50 yards or so away, where they could check their material, and they had to run like hell from one room to the other. And Fermi, who, as I said, was a very competitive individual, claimed to be the fastest runner. One of the things they did was to irradiate rhodium. Now, rhodium has 45 protons in it, and it has 57 neutrons in general, or 58 neutrons. When you put another neutron into rhodium, something very peculiar can happen. That neutron, that extra neutron, can decay. It can turn into a proton. Now, that's 0 charge going to +1 charge. That's not allowed. So it also makes an electron, which has a negative charge, so +1 and -1 give you 0. And then there is a third particle, which I'll ignore, which turns out to be extremely important, called an antineutrino, but I'll leave that out for the time being. Now, what happens then is that you go from 45 protons to 46 protons. You go from rhodium to palladium. That's called alchemy, something that people tried in the Middle Ages to do for hundreds of years. So finally, you can make alchemy. In fact, you can turn lead into gold, except it's much more expensive than going out and buying gold, but you can do it. So the chemical analysis showed, rhodium became radium, iron became copper, etc. Cobalt, I'm sorry, etc. When they got to element 92, uranium, I don't know if you can you see that down there? Okay, when they got to element 92, notice there are elements above uranium, and the numbers are all in white. And that's because none of these elements exist in nature. And I'll talk about why that is, including element 100, which is called fermium in his honor. The list goes up to 115 or so in these days, much higher, including 109, which is called meitnerium, after Lisa Meitner. When they got to uranium, they didn't know what the chemistry was. Now, since rhodium became palladium, that iron became cobalt, etc., nickel became copper, they thought, well, maybe uranium became number 93. And that was a great discovery. But Fermi, and he wasn't sure, and Fermi was a very cautious man. He was a good scientist, and so he did not claim that. But politicians are not necessarily very cautious, as we're learning to our dismay these days. And so one of the Italian senators splashed the news of the discovery of a new element all over the fascist newspapers as a triumph to the existence of fascism. Well, it turns out that that's not true. The reason these elements do not exist is fairly simple. A nucleus is tiny, even compared to the tiny atom. And a human hair is about 1/10 of a millimeter across. And across that 1/10 of a millimeter, you can put 1,000,000 atoms. Okay? So they're pretty small. But the nucleus is between 10,000 or 100,000 times smaller than that. So it is really tiny. And it has protons inside, 26 in iron, 92 in uranium. And positive charges repel. Okay. So why do the nuclei, and therefore atoms, and therefore us, why do we exist if there's this tremendous repulsive force going on? Well, the answer has to be that despite this repulsive force, there must be an attractive force which is even greater. And so, since this attractive force is responsible for the nucleus, I'll call it the nuclear force. Or since it is very strong, I could call it the strong force. Either name is okay. In fact, it is 137 times stronger than the electrical repulsion. However, the strong force is very limited in range. It only acts to the neighboring particle, so that two protons will stick together if they are right next to one another. But two protons will repel no matter where they are in the nucleus, because the electrical force is basically infinite in range. And so now the purpose of the neutron, and the reason we chuck in more neutrons as we go up in weight, is because the neutrons push the protons farther apart, and therefore they lessen the repulsive force. That's very clever, nature. But as we go higher and higher in number, oh, there's meitnerium, there's 109, good. This goes up to 111, but it really goes up a few more these days. Now, as you go higher and higher, the repulsive force keeps getting bigger, but the strong force, the attractive force, never grows. It always works only on the neighboring particle. And so by the time you get to 92, these two forces become approximately equal. And when you go to 93, the repulsive force wins, and therefore all of these, all of these elements here and here don't exist in the Earth's crust, because the electrical repulsion wins against them. Now, in fact, Fermi had not created element 93, as we shall see. My last basic point for today, I'm sorry I go over. Two of his students, Eduardo Amaldi, whose picture we saw, and Bruno Pontecorvo, both of whom are incredibly famous, were working with various metals and testing them. And what they did by bombarding with neutrons, and they did this by making by making the metal in the form of a hollow cylinder and putting this radium beryllium source inside the cylinder to make the neutrons. And they found, and then they put the whole thing inside a lead box to protect themselves from all the radiation. What they found is if they put it in the middle of the box, they got a given effect. If they put it in the corner, they got a different effect. Completely crazy. How could that possibly be? Fermi suggested doing the experiment outside the lead box, and the results were even more peculiar. The wooden table made a big difference. Putting a sheet of lead up made no difference at all. Fermi said, look, lead doesn't make any difference, but lead is a very heavy substance. Let's try a substance with light atoms. And so they took a block of paraffin, hollowed it out, and put the thing inside, and it went nuts. I mean, they just made tons and tons of radioactive elements. Now, the source produced what are called fast neutrons. Okay? Fast neutrons are neutrons whose speed is about 1/10 the speed of light, or about 30 million meters per second. Slow neutrons, which are very important in the world, which no source makes, but which can be made, are and did not exist at that time, are much slower. They move at a mere 30,000 meters per second, and that's really dawdling. That's a mere 100,000 kilometers an hour, quite slow for elementary particles. Fermi came up with a solution to this, and to explain that, lead is a very heavy element, as I said. It has a mass of 208, basically, 207 nuclear particles. If you throw a cricket ball against a bus, the cricket ball will rebound. The bus won't move very much because it's heavy compared to the cricket ball. So the cricket ball will deflect. It'll come off with the same speed, but in a different direction. But if a cricket ball hits another cricket ball, then both balls rebound, and the rebounding cricket ball has less speed than the incoming cricket ball than it had when it was incoming. So they both recoil with some energy. So if a neutron hits a heavy nucleus like lead, it's just like a cricket ball hitting a bus. It just bounces off in a different direction. But let it hit a proton or a carbon nucleus, which weigh basically the same thing as the neutron, and they both recoil, and the neutron that recoils has a much lower energy than it had. Now, moving through a big block of material like the paraffin meant lots and lots of collisions, and so the neutron was slowed down in going through. But a slow neutron has, as it dawdles at a mere 100,000 kilometers per hour, dawdles by, at the time when Los Alamos was created to build the bomb, Britain was suffering the Blitz, and much of continental Europe was occupied by Nazi Germany. The scientists in the UK and in the US were largely men, but not all. There were some women involved as well. Were very well aware of the caliber and the abilities of their German colleagues. Due to the Nazi threat, 111 scientists and mathematicians had left Europe. Among them, there were 33 Nobel Prize winners, among that 111, which is quite a remarkable number. Some came to the UK, mostly they came to the US. There were a few non-science people who are very famous, such as Hannah Arendt, Kurt Weill, Ludwig Wittgenstein, for example. Many of these people were Jewish, fortunate enough to get out. All the scientists were aware that nuclear fission had been discovered in Germany and that Germany was ahead. The fear and the pressure on people was enormous. They worked as hard as they possibly could under extreme handicaps, and used for over 70 years. And there are a few people in this room, including me, old enough to remember when they were used. But the two bombs that the Americans used on Japan were virtually firecrackers. They are so tiny compared to what exists today. I worked for several years on problems of weapons non-proliferation, but nonetheless there are at least 8 countries in the world today which possess nuclear weapons. Their importance, their growth is such that perhaps they have prevented war, because, or at least they have prevented world wars. There have, at least so far, there have been no conflicts between the major superpowers because people have come to realize that these weapons there are no winners in that case. There are only losers. These weapons kill everybody. The situation could be and could have been and still can be very different, and I want to outline this, of course, and the problems involved. Now, I started my university studies back in the 1950s, and every professor in every class I ever took or every research project on which I ever worked had been doing research during the Second World War. They worked on things like the Norden bomb site, or on radar development, or on the development of shaped charges which allow the piercing of armor on the fronts of tanks, or, of course, at Los Alamos on atomic weapons. The pressures at that time on people are not easily understood by generations too young to remember those days, and I'm absolutely delighted that there are a few people here who are too young to remember those days, because they need to understand. But the threat of Nazi Germany, of course, was enormous. The war was seen really, and probably really was, seen as a means of determining the future of civilization. There was a pandemic of man-made death in the 1940s. The British and the Americans were fighting in the Pacific and in North Africa.
Development of science education in South Africa. So he's one of the volunteer coordinators of the Institute of Physics Africa program. So let me, without further ado,
well, thank you. It's always a delight to be back in this wonderful country, of which I am so extraordinarily fond. I want to speak this week about weapons of mass destruction. This is a topic of enormous importance because there exist on Earth enough nuclear weapons to kill every human being on the planet several times over. Okay? Moreover, there is a man who will take control of about 5,000 of these next Friday, who has first encouraged proliferation by encouraging Japan and South Korea to have nuclear weapons, and who has stated that we have so many of these things, why don't we use them? No such weapons have been. Those at Los Alamos were very well aware of the awesome scale of the weapon that they were building. But they ceded control over the development and the use entirely to the military. And they probably had no choice in doing that because the amount of money invested was truly enormous. In today's terms, the U.S. put approximately $40 billion into developing the atomic bomb. And I doubt that the U.S. government would have given that amount of money to a group of weirdo scientists. But still, the control was given up without a great deal of thought. A few people, as we shall see, did object and did think, and many people suffered serious moral crises after the war when the consequences of what they had done became obvious. I worked with a man in about 1970 who was a major player at Los Alamos and whose life was basically destroyed. He never did a decent piece of work after that, although he was an extraordinarily bright and very nice man. The